You can start, Alvaro, when you want.
Okay, so we're good to go now. Okay, yeah. So okay, so I can introduce the speaker already, right? Or that's what you.
Yes, please introduce the speaker.
Okay. Okay, so I see there's a few of you already there. So thanks a lot for coming to this session of Quantum Spain's online seminar. Yeah, so today we're very happy to have Michael Vasmer, who's going to tell us about quantum error correction, in particular with constant overhead. Although I believe Mike is going to also give some sort of introduction to error correction in the beginning of the talk for those of you who are not so familiar with it. Which is of course one of the main challenges of quantum computing. So we're very happy to have an expert like Mike here. And yeah, just to give an idea of who he is. So he actually spends part of his time in industry, in particular in Xanadu, and also part of his time in academia. So both in Perimeter Institute, where we actually overlapped, and in IQC in Waterloo in Canada. Okay, so I guess please, Mike, the room is yours.
Great. Yeah, thanks a lot for the nice introduction, and thanks for the invitation to speak here. Yeah, I'm looking forward to telling you about quantum error correction, and as Alvaro said, I'll give you a bit of an overview to start with, and then I'll also talk about some of my work later on. But I want to encourage you as well to please interrupt me with questions if things are not clear. Okay. So I wanted to start with a kind of high-level picture of why should you care about quantum error correction as a topic. So I think there's a few reasons. So one of the main ones is that the current quantum computers we have, their performance is severely limited by noise. It means we can't run deep circuits, and it's very difficult to get good data out from them. And quantum error correction has the promise to enable kind of scalable quantum computation for applications. So if you want to run all the applications you've heard about, like Shor's factoring algorithm, or a chemistry simulation, or some kind of optimization problem, then with quantum error correction, the promise is to achieve scalable quantum computing to do this. But there's a catch, is that currently the kind of space and time overheads of quantum error correction are very high. So by that I mean, when we do quantum error correction, as you'll see in a bit, we have to kind of increase the number of qubits in the device to add some redundancy in a way, and we also have a kind of a time overhead cost. And at the moment, you're thinking, if you want to do kind of a useful algorithm, you need maybe on the order of 1,000 qubits. But then when you want to do quantum error correction on top of that, you end up needing kind of like 1,000,000 qubits or something like this. So it's a big overhead, and one of the big focuses in my research in the field is how to kind of reduce this overhead. And quantum error correction is a big focus, I would say, these days in quantum information, both in academia, in government, and also in industry. To give you a few examples of this, here's a screen cap of the Google CEO kind of doing a blog post about their progress in quantum error correction. And then, so a big focus in industry. And then also there's a recent news in the last couple of weeks that the Australian government invested like $1 billion into PsiQuantum, who is a quantum computing startup company with a big error correction focus. So I think, yeah, so we've got a lot of interest and money going into this field, and I think it's justified, because I think this is one of the main kind of roadblocks still there to achieving scalable quantum computing. But even if you don't kind of care too much about quantum computing, I think there's also other reasons to study error correction, in that it has surprising connections to other fields in computer science and physics. For example, I won't be able to talk about this in detail, but there's a nice relationship between error correcting codes and topological phases of matter. And there's also connections between error correction and black holes, and then kind of complexity theory conjectures as well have deep connections with error correction and fault tolerance. So I think it's a field that has a lot of kind of potential for impact, but also has these nice connections with different areas of physics and in quantum information and beyond. Okay, so now that I've got the motivation out of the way, hopefully piqued your interest, I'll give you just tell you how the talk's going to go. It's going to be in 3 parts. The first part, I'm just going to give you an overview of quantum error correction from kind of 101. And then I'm going to focus a bit onto a specific aspect of quantum error correction, which is called the decoding problem. And then to end with, I'll talk about one kind of solution to the decoding problem that's efficient, which is called single-shot error correction. I'll define all these things as we go. But yeah, let's get started. So I think I was telling Alvaro just before the call that I gave a talk last week for a machine learning audience, giving some quantum error correction kind of overview. So I think this first slide is probably a bit basic for this audience. We'll skip through it quickly. So we have quantum bits, we have qubits, and then we have Pauli matrices. And all I want to kind of say here for us is that for me, the Pauli matrices, I'll think of them as quantum errors. So a bit flip is something that changes the 0 to the 1 state, and a phase flip changes the relative phase. And then the y error is like the combination of a bit flip and a phase flip. Okay, so then we have we go from 1 to many qubits, and we have some n-qubit Hilbert space. And we also we define, probably reminder for everyone, the n-qubit Pauli group, which we just generate by tensor products of the Pauli matrices and the 2x2 identity. And then now we can talk about our quantum error correcting code, which abstractly is just a subspace of the Hilbert space. So what I'm going to do is I have some information, I want to encode it into a subspace. So abstractly, a quantum error correcting code is a subspace, but let's make that concrete, and we'll talk about a family of codes called stabilizer codes. These were proposed by Gottesman, and they're really the most widely studied class of quantum error correcting codes. And if you know a bit about classical coding theory, they're like the quantum version of linear codes. So the way the definition goes is we take the Pauli group, script P n, and we take a subgroup, S. And this subgroup has two properties. It's abelian, so all the elements of the subgroup commute with all the other ones, and also minus identity is not in the subgroup. From this, we can define our code subspace. So we take all of the states in our n-qubit Hilbert space such that they're the +1 eigenstate of all of the stabilizers in our stabilizer group. So we'll do an example of this in a second, but there's a few important things about this subspace. So one is the dimension of the subspace, and this kind of tells you how the dimension tells you how many encoded qubits you can store in your subspace. And yeah, the rank of the stabilizer group is just the number of independent generators. Okay, yeah, so that's the abstract definition. We have the code space here. Yeah, and then we need to, so at the moment I've told you about how to encode some information, but I need to tell you how to kind of process the information, because at the end of the day, we're interested in computation, not just quantum memory. So just to remind you of a definition, we have the normalizer of this stabilizer group in the Pauli group. What's this? It's just you take all the Pauli operators that commute with everything in the stabilizer. So this clearly contains the stabilizer itself, because we define the stabilizer to be an abelian subgroup, but the normalizer in general can be bigger than the stabilizer. And this is something we can use to define what's called logical operators or non-trivial logical operators. So an operator in the normalizer of the stabilizer group that's not actually a stabilizer, so with like as written here, this has this kind of, it preserves the code space, it preserves the encoding, but it maps one encoded state to another encoded state. So it's like an encoded logical operation. And then there's an important concept now, is that something called the code distance. So what we have is this number d, which is equal to the minimum weight of all of these non-trivial logical operators. So any operator that can kind of change one encoded state into a different one, we want to understand what the minimum weight operator that can do that is, because this is kind of telling us about the protection the code offers to us. Because if you think about the environment kind of doing some kind of daemon doing errors in your system, then it has to do at least d errors to kind of change one code state into another. So this is a way of quantifying how well your code protects you against errors. And then we often summarize the parameters of a code in this kind of shorthand. So we have n, k, and d, where again, n is the number of qubits, the number of physical qubits, K is the dimension of the code subspace, or the number of encoded logical qubits, and D is the code distance, which, as I said, tells you about how well your code protects you against errors. And clearly, you know, K is less than or equal to N, and D is also less than or equal to N. And in general, the kind of name of the game in quantum error correction often is we want to find codes where we have, for some N, we have like a large K and a large D. So we have good parameters. Okay, so that was some kind of more technical content. Now I want to tell you about an example. So we'll talk about something called the 422 code, which is a small quantum error correcting code, but nonetheless is still quite interesting and useful in practice. So this is a code where we encode two logical qubits into the state of 4 physical qubits. And we have this stabilizer group, where this notation just means like X acting on the first qubit, X acting on the second, X acting on the third, X acting on the fourth. And then we have this 4-body Z operator as well. And these angle brackets, I'm just writing them as these are the group generators, but the group is, you just take all the products of these to get all the group elements. And yeah, so you can see you have 2 generators here. So we have two encoded qubits. And then I can also write down the logical operators for you here. So the notation I'm using is this overline X bar denotes an operator acting on the logical qubit. And then on the right, I have how it acts on the physical qubits. So you can check that logical X1, well, that commutes with the stabilizer generators up here, because X operators, they commute trivially because they have the same Pauli label. And then the X operator commutes with the Z-type stabilizer because they have, although they have different Pauli labels, they kind of overlap on an even number of qubits. So you get 2 anti-commutations, which is just equal to a commutation. And then we have, so these are all the logical operators. And then you can notice that they have the correct commutation relations to represent the algebra of like two qubits. So, you know, X1 bar and Z1 bar anti-commute, but then Z1 bar and X2 bar commute, for example. And you can see that these operators, although they commute with the stabilizer generators, they're not in the stabilizer because I can't build them by taking products of those 2 stabilizer generators, the 4-body X and 4-body Z. And so one thing I want to stress actually is in quantum error correction with stabilizer codes, kind of the power of the formalism is that you can deal with this abelian group and you can deal with the generators of the group, which is in general not too many objects. And you don't really have to think about the encoded states themselves because the encoded states will be a massive superposition over many terms, but it's kind of easier to deal with the stabilizer, these Pauli operators. It's kind of known as the like Heisenberg representation sort of. But you can also write the encoded states. This all defined. It's just often easier to think about the stabilizers instead. But in this case, we have these kind of encoded states. So again, I'm using the bar notation to denote the encoded qubits. So the 0, 0 encoded state has the form of it's a GHZ state on the physical qubits, and then you can form the other encoded states by like acting with the relevant logical operator. So to get this second one here, I just applied logical X1, this X1 bar to the 0, 0 state, and then we get this. Yeah, so that's the 422 code, and it's a nice example that I think illustrates the formalism. Okay, right. So that's the end of the very fast introduction to quantum error correction. So before kind of moving on, I just want to see if anyone has any questions at this point. Yeah, I think I see one here. Yeah, I'm just going to look at the chat. So any of the logical operators act on the 4th physical qubit. Is it a typo or is it intentional? Yeah, that's a good question. So the logical operators I've written down here, you notice that none of them actually act on the 4th physical qubit. So kind of what is the 4th physical qubit doing here? Is it necessary? Well, so what I want to, one thing to start with I can say is that these logical operators, they're just like one representative, but I could form another representative of the same operator by multiplying by a stabilizer. So I can also make a logical X1. Let me just, I can start writing a bit on the thing. So there's also a logical X1 that looks like, like this, because what I've done there is I've acted with the X stabilizer generator on the logical X1. And so this one kind of does have support on the 4th qubit, but nevertheless, there are these representatives with no support. But what I would say is that to define this code, you need to have like a set of stabilizers. And if I just had like X1, X2, X3, and Z1, Z2, Z3, then they wouldn't commute. So I sort of need the 4th qubit to make them commute. Okay, so I hope that answers that question. Then we have a second one, which is how would you compute the D in this example? So in this example, all the kind of spaces are quite small. So like the number of possible Pauli operators is quite small. So I can just like exhaustively enumerate them all and check like for each Pauli operator, does it commute with the stabilizers? And then is it a stabilizer? And then I can just minimize over this. But in general, computing the code distance of a quantum error correcting code is a hard problem. You know, even in the classical case, the analogous problem is NP complete, I think. So in general, there are kind of heuristic algorithms that can be used to do this, and there was various ones using kind of often using kind of insights from classical coding theory. But for an arbitrary, and this is often like the difficult thing with when you propose a code family as well is kind of proving that it has a certain distance bound is often quite hard. Okay, thanks for the questions. I think can move on now to the second part of the talk, which is on the decoding problem. So I want to stress that, yeah, I'm going to use decoding in the kind of quantum error correction subfield way that I will use it. So I'm going to explain exactly what this means because it's kind of slightly overloaded the term. So I first want to talk about Pauli errors. So I'm going to consider error models where we only have Pauli errors, and I just want to justify that slightly. And the justification you'll get is that the Pauli group provides a basis for n-qubit errors, n-qubit unitary. So you can kind of express unitary errors in the Pauli basis, and then when you measure stabilizer generators, you sort of project into the Pauli basis. This can be made a lot more formal, this argument. If you're interested, I can give you some references. But this is why in quantum error correction, we often use a Pauli error model and then kind of make this assumption. So the kind of channels we'll be interested in, for example, is like this bit flip channel, where now I've changed to using the kind of a density matrix, but this is just a channel that with probability 1 minus p does nothing, and with probability p applies a bit flip. And then stuff like, you know, I'm sure everyone's seen these before, the depolarizing channel as well, where it's kind of similar, except now with probability p, I just pick randomly one of the 3 possible Pauli errors and apply that. So these are the kind of channels you can think about. And now I want to define something called the error syndrome. So let's kind of go back. So we have a stabilizer group, and we have an associated NKD code. And then I'm going to make an assumption now. So let's assume that we have an operator E, which is in the Pauli group. This is E is going to stand for error. And now the weight of this error, weight of E, is less than D, the code distance. Okay. So now my claim is either this error is in the stabilizer group, or there exists a stabilizer such that this error anti-commutes with it. How do we see this? Well, let's kind of draw a picture. So we start with the Pauli group, P sub n, and then the stabilizer group is some abelian subgroup inside here. And then the normalizer here is like this kind of, it contains the stabilizer, but it can be slightly bigger. And so we've kind of characterized the normalizer. So the code distance here is saying that everything that's in the normalizer but is not in the stabilizer, so that would be like things like in here, this has a weight at most, at least D. So if we have an operator with weight less than D, either it has to be in this stabilizer part or it has to be outside of the normalizer. Those are the only 2 possible options. And so what does that tell us? That tells us something quite useful. So let's imagine we have this state here, which is E acting on an encoded state psi bar. So this is kind of our state, and then imagine we act with the stabilizer S that anti-commutes with E on this state here. Well, then we can just anti-commute it through, and then this S on psi bar is just psi bar because of the definition of the stabilizer code. So then what you've kind of shown is that this E psi bar is a -1 eigenstate of this operator S. And so you'll recall that this is different from this is not what we wanted. That our encoded states are supposed to be +1 eigenstates of the stabilizers. But now what we can see is by basically by measuring the stabilizers, we're going to be able to get some information about the error. So let's make this a bit more concrete. So what we do with quantum error correction with the stabilizer code is we measure a generating set of the stabilizer group, and then the error syndrome is defined to be the list of the measurement outcomes. So in the case when I have all +1 outcomes, that means I've just got an encoded state. But sometimes I will have, sometimes I will have a -1 outcomes if errors have occurred, and this tells me some information about the errors. But yeah, I'm just going to let's go back to the 422 example a bit here, because last week this was a bit confusing. Is someone asked how do you actually measure these stabilizers? So I want to give you an example of this. So let's imagine we have this is our 422 code. So we have some encoded state here. Now I want to measure my, let's say my X type stabilizer. So what would I do? I would introduce an ancilla, and then I'm going to do this. And then I will measure this like this. So this is like this is just a standard circuit to do these kind of measurements. And so what I've done, I've introduced this ancilla. I do this controlled. You see, I'm sort of applying a controlled stabilizer because I just do X, 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 and then I measure this in the X basis at the end. And you can kind of show just using, this is basically a phase kickback type of circuit, that you will get the eigenvalue of this the stabilizer we wanted to measure here, which is x1, x2, x3, x4, and you will get this eigenvalue, and this is like a non-demolition measurement. So you haven't like collapsed the superposition of the encoded state. You've just done this measurement. And so you do this for all the stabilizer generators, and then you get a list of measurement outcomes. And then in the case where you have no errors, you'll be +1, so that's great. But then usually you'll measure some -1s, and then it doesn't tell you like exactly what error has occurred, but it gives you some information, because what you know is like, okay, the error that occurred anti-commuted with this stabilizer. So to kind of stress this, the way you can think about this is we have this stabilizer code, we measure M stabilizer generators. And so the decoding problem is we have this error syndrome, which is, I'm going to write a sigma of E. So E is the error and sigma of E gives you the syndrome. And this is kind of a vector of -1 and 1 entries. And then the output that your algorithm, your decoding algorithm should give you is some recovery operator, which is in the parity group. And then you want it to have the same syndrome as the error. So you just find a recovery operator with the same syndrome, and then essentially you use the fact that because of the parity operators and the kind of the structure of the algebra here, this will just always be, well, I should say it should be like it will be in this notation 1, 1, 1, 1. Because they have the same syndrome, so they sort of the -1s will cancel, and so then after you've done this, so we have our recovery operator, and then the overall operation we've applied is R times E, because the environment did this error E, and then we applied this recovery operator. And so then we're going to successfully solve the decoding problem if R times E is in the stabilizer group. And so what that means is that this operator has acted overall, the action on the code space has been just a logical identity. Because you can think of the stabilizer operators as exactly being logical identity operators, because they don't change the encoded states. So the decoding problem, again, we just measure the stabilizer generators, we get the error syndrome, we find a recovery operator such that the syndrome of this is the same as the input, and then we've been successful if the overall effect of the error times recovery is just is trivial as a stabilizer. Okay, so this was all a bit abstract, but now I'm going to try and give you an example of this with something called the surface code. So I decided to try and like live draw this part. So let's see how it goes. So we'll consider like yeah, the surface code. So we can consider, I'll draw like a kind of small example, but this code is like a general family.
Mike, there's a question in the chat. So can
Yeah.
R be equal to E?
Oh, thanks. Yeah, that's a good. Actually, yeah. So let me go back. That's a very good question. So yes, R can be equal to E, and in that case, you will have solved the decoding problem successfully, because then R times E is just identity. So that's always a stabilizer, actually, because the stabilizer group is always going to contain the identity. But actually, this is the main difference between classical coding theory and quantum coding theory. Because in quantum coding theory, I don't need to know exactly what error occurred. I just need to kind of estimate it up to a stabilizer, and that's enough. Whereas in classical coding theory, you kind of want to find the actual code word. But in quantum codes, there's this degeneracy kind of property where many errors can have the same syndrome. And so this gives me kind of extra freedom in the decoding problem. Okay, so let's go back to this surface code. So I'm going to use some notation. So I'm going to just draw this little picture very quickly. So in this code, we have this kind of structure. So each of these little dots is going to be a qubit, and these are the physical qubits of the code. And then we have these stabilizer operators. So the way it works is, so we have like something like this. The blue ones are going to be Z operators. So we act with, I'm just telling you what the stabilizer generators are. So the blue ones are a Z type, and the red ones are X type, like this. So on this lattice here, you see I have 9 physical qubits, like this, and then I have these stabilizer generators. So this one here is like a 4-body X term, as is this one. This is a 4-body Z, a 4-body Z, and these ones are kind of these boundary stabilizers are just weight 2, but they have a similar definition. So this would be a weight 2Z, for example. Okay, so this is like a very well studied and useful family of error correcting codes. It was the one used by Google in the experiment I showed earlier, actually. And these codes, so we have this stabilizer code definition, and in general, so this code, you can work it out, has parameters 9, 1, 3. Because you can kind of see that we have 9 physical qubits, we have 8 stabilizer generators, and then you can kind of verify the distance is 3. Okay, and then what does the decoding problem look like in this kind of thing? Well, so I'm going to draw like a kind of a bigger sketch. So this code, I've given you the kind of definition, but what you want to imagine is this is like defined on some kind of D by D lattice, and so you can kind of grow the size and you get a much bigger code. And this allows you to kind of like change the protection of the code depending on what you need. And then what you end up doing is so one thing that's nice about these kind of codes, where you see I've got this division of X and Z operators into, so I have operators that only act as pally X and operators that only act as pally Z, is that I can kind of consider the decoding problem separately. So let's consider just the phase flip channel. Like this. And then, so I will have like, so I'm going to have some errors, right? So I'll draw them in red. So imagine this is like a big lattice now with all this like checkerboard, but I haven't just drawn in the details. So I have some kind of chain of Zs. These are just some like Z errors. Okay, so imagine this has occurred in our lattice. And then pictorially, what the decoder will see. So we measure all the stabilizer generators. And then what it will see is you'll get like a -1 outcome at the ends of chains is what happens. So each of these -1s kind of represents a square where I've measured it and I've got a -1 outcome. And so in this problem, what you see is just like you have these chains of errors, you see their endpoints. And so then the solution to this problem, well, a good solution is you take these endpoints and you just find the shortest kind of path that connects them in the lattice. And so the decoding problem in this code can be kind of mapped to just like a graph theory problem where you have some, you can imagine it as having some marked vertices, and then you want to find the minimum path between them. And so this is quite sketchy, what I just drew for you, but there's some good news as well, is that as part of the talk I gave last week, I actually prepared like a tutorial notebook on how to decode the surface code. So if you want to know more about this example, you can scan this QR code, and it should take you to my GitHub, where there's like a tutorial on how to decode this quantum code. So yeah, I'll just leave that up for a second there. But this surface code, it has a very nice properties. It has a high error threshold, and it's got this like planar layout, which makes it very compatible with kind of architectures where you've got 2D connectivity of qubits. Okay, great. So, okay, the last thing I want to say in this section actually is about maybe a drawback of the surface code, though. So far, I've kind of been assuming an error model where the circuits I use to measure the stabilizers are perfect, or there's no errors in my measurements. They're always reliable. But we know that in a real quantum computer, this is a very bad assumption, in that measurements are often quite noisy. So we have to understand how to solve the error correction problem when we can't actually rely on our measurements. And the standard approach to solving the decoding problem with unreliable measurements is just to repeat the measurements d times. And in the surface code case, what you kind of go, what I was drawing on the last slide was a 2D graph theory problem, and then when you do d rounds of measurements, you kind of lift this to a 3D problem. And again, this is kind of covered in the notebook if you want to have a look at that. And the kind of standard assumption is that I want to run an algorithm eventually on my fault-tolerant quantum computer. So I do logical gates as the algorithm tells me. Then after every gate, I have to do error correction to make sure errors don't kind of build up too much. But this is a bit of a problem, because if I'm doing d rounds of error correction after every gate, then my whole clock speed has been slowed down by a factor of d, and this can be, you know, substantial in practice. In that it's kind of like d is like 30 or so. You think to have like do Shor's algorithm or something. So I'm paying this price of, and this is like the slowdown is like d times the measurement time, and this, you know, when you're thinking of doing like 10 to the 15 gates or something, these things are not insignificant. And so this is a problem with like the standard surface code, and this is one of the overheads of quantum error correction I was talking to you about. There's like a space overhead that we haven't really talked about, but there's also this time overhead kind of associated with error correction. What I want to tell you about in the final part of the talk is something about how some work I've done and others have done on trying to reduce this time overhead of error correction. Yeah, but before we go there, I think it's a good time to pause for questions, and yeah, give you opportunity to ask anything about the decoding problem or the surface code.
So maybe just to clarify, it's not an accident that this d is the same as the distance, or is it not?
Yeah, sorry. Yeah, I should have written that down. Yeah, so we're kind of, I'm assuming I've got like an NKD stabilizer code, and then I want to do error correction, and now my measurements are unreliable, and a kind of standard way to make this work is you just measure the stabilizers d times instead of just once. And so then you see this is kind of annoying, because the better your code is, like the worse, the more time overhead you end up having here. So it's not ideal, really.
Thanks.
Cool. Okay. Yeah. Let's go on to the last part of the talk now. So there's this nice framework of single-shot error correction. What does this mean? So we can define a single-shot error correction property, and this is actually work done by Hector Bombin. So in this kind of codes with this property, instead of repeating my stabilizer measurements d rounds, one round of measurements suffices for doing error correction, even if the measurements are unreliable. So codes like this have kind of some special property that has extra robustness, let's say. And there's kind of a few examples of codes where this works, actually. So in follow-up work, Hector kind of looked at this gauge color code model that has this code has this property, and it's kind of very nice. One of the first example, I think. And then it was realized that there's certain other classes of code, so hypergraph product codes, and so depending on the inputs you can get, code with a single shot property. And then I want to tell you about a code that I worked on that has this property. So this is joint work with Alex Kubica. Okay. Yeah, so this part, I'm going to try and explain this code to you, but I have to be quite high level because there's some details to get through, but I just want to kind of give you a flavor of how the single shot error correction property works in this code, because I think it gives you kind of a reasonably clear example of how you can get away with one round of measurements, even if they're unreliable. So now we have to go to it's another kind of topological code, so it's defined in some kind of as a lattice model. But now we're going to go to 3 dimensions. So we take like an L by L by L simple cubic lattice, and you terminate it with some boundary conditions, but that's not really important for now, where we can think about the bulk. And in this lattice, so we kind of associate our physical qubits with the edges now of the lattice, and then the stabilizers of the code are like associated to these cells. So I have a cell of a cubic lattice, and you can notice that one of these things has 12 edges, and let's say this is like the red one. So this would be like there'd be an operator that acts with like X on all of the different edges of this cube, because these are where the qubits live. I won't draw them all, but you kind of get the idea. And we have the X and the Z, the red and the blue, like the previous example. Okay. This code has parameters that look a bit like this. So we have kind of, because we're defining it on this L by L by L lattice, we have like order L cubed physical qubits. We get one encoded qubit, and we get codistance of L. And there's one complication with this code that I'm not going to have time to go into formally, but this is actually an example of something called a subsystem code. And in this type of code, we, instead of measuring the stabilizers directly, we kind of break them up into smaller pieces and measure the pieces. So we measure, I'm just going to call them checks, but they're not the stabilizers. So the checks would be like these 3-body operators. So you can see that this is like in gray here, we have like the cubic lattice, and then we've put like these white dots where the qubits live. And instead of measuring the whole 12-body operator, I'm going to measure just the 3-body kind of pieces at the corners. So for each corner of the cube, I have this 3-body operator. So one there, etc. So there's 8 of them for the 8 corners. And so the red ones are again X, and the blue ones are Z. And so I have to measure these instead of measuring the stabilizers. And yeah, so the nice thing is that I can form the stabilizers from the checks. So the stabilizer operator was like a 12-body operator acting on all the qubits that live on the cube. And then, you know, if I take the product of this one here, this one here, this one here, and this one here, I'll get the stabilizer back. So I've broken it up into smaller pieces, but I can recover the stabilizer from the smaller pieces. Okay, but why have I done this kind of trick? Well, there's now something that's quite interesting that's happening. So I can this operator, the product of these 4 checks and these 4 checks is the same, and the same with the product of these 4 and these 4. So this is like a local kind of redundancy in the generating set of the checks I chose to measure. So I have like different combination of checks that should agree, and this gives me like some consistency checks essentially on the measurement outcomes, because I know you think when I'm doing error correction, I measure each of these operators, but I have this constraint that the product of these 4 should equal the product of these 4. So if those products don't match, then I know that something's gone wrong in my measurements. So you can kind of see how this code is allowing me to, basically I'm measuring some overcomplete set of checks, which allows me to see when some measurements have gone wrong. So in this code, I have these local redundancies, and then there's also like redundancies around a vertex, but I won't go into those in too much detail. But what I want you to think of is I do these measurements, and then there's some like local checks which allow me to see when my measurements have gone wrong. Okay, so in a like, this is the most technical part, so please bear with me. But let's see if we can get through this. So I just want to give you a very high level understanding. Okay, let's just before we go, there's a question. So the question is this 3D code related to the HAR code? So I think, I mean, not closely. So this code is like technically it's some kind of subsystem code where I can gauge fix it to some kind of stabilizer toric code type model. So what I want to say is that kind of excitations in this model are like string-like again. So Haas code has this property of like fractal excitations, and so this is quite different from what this model has. So although they're both kind of 3D stabilizer or subsystem codes, the kind of topological order that's kind of here is quite different, I think, because this code has no kind of like fracton order or anything like that. Okay, yeah. So let me try and like guide you through this a bit. So right, so this is what the decoder sees in the first step of the algorithm. So okay, what do the colors here represent? Well, so these operators that I measure, you remember I had two sets of let's say X checks that should multiply to give the same thing. So what I'm going to do is I'm going to introduce a color to like label the two sets. So that's what the yellow and green are. And the constraint that I showed you where these products should be the same, in this kind of dual picture where you associate instead of measurement outcomes to edges instead of faces, you do it this way because then you have the constraint means that the measurement outcome should form like closed loops. So you can think of this as some kind of like flux type picture. And so in the case when I have no measurement errors, my kind of configuration I should all be like closed loops, apart from some complications at the boundary, but don't worry about that. But then in the case where I do have measurement errors, I kind of, instead of measuring closed loops, I'll see some like broken loops like this. And so what these dots are here is like the breakpoints of the loops. And so, but again, you can kind of see that this decoding problem looks kind of a bit similar to the 2D surface code one in that all I need to do to correct this problem is I have these like loops here, these breakpoints, and I know the loop should be closed. So I just kind of like join them up, and you can see that that's what's happened here. I join them up like this, and then now I have like a valid measurement outcome. So this stage is when you correct the measurements because you see that like, okay, I know if all my measurements are correct, the loop should be closed. They're not closed, so I just close them, and now I have something that kind of passes all my measurement, the checks on the checks, let's say. And now there's like one further step because now we still need to like find the stabilized eigenvalues, which we can do from just taking products of the checks, and then we can just correct the error, do the error correction problem for the stabilizers, which is kind of like the toric code again. So in this case, actually, you can show that like where these loops, where the color changes, will be exactly where you have -1 eigenvalues of the stabilizers, and so that's what we've kind of put with these dots here. And then again, you basically have a matching problem. So we can define a graph theory problem, and then we want to find the shortest path between these vertices. And that's sort of what these blue things are here. So what I want to stress is that, you know, you do all this measurements, and then you see this kind of mess. You correct this. And then at the end, this is your recovery operator, these like blue lines. But what's the good thing that's happened here is that because of this like structure of the measurements here that tells me when some of them have gone wrong, it means that I don't make a massive mistake when I do this recovery operator, because I can kind of fix up the measurement outcomes using these redundancy checks, and then I can do my error correction problem sort of safe in the knowledge that my measurements are essentially reliable. So that's, I just wanted to give you like a very high level overview of how this works. Yeah, there's many more details in our paper, and we also had a follow-up work where we put some code for simulating this some numerical code for simulating this online, so you can also see that. Okay, so I think I'm getting quite close to the end, but I'll just flash up some numerical results we did, which I think are quite nice. So what you're seeing here is like an error threshold plot. So you can think of this L here as basically being the lattice size, so it's like equivalently the code distance, and then this is like the bit flip and measurement error rate. And then this is the, so we have an error model where all of our qubits have a bit flip with probability P, and it's identically and independently distributed. And also the measurements sort of fail with probability P. So, you know, instead of measuring, like if I should have measured a -1, I get a +1 with probability P. Then this thing here is the logical error rate. So basically what I'm doing is like doing a simulation of encoding some information, then letting it kind of sit for a while, then trying to correct errors and see if I managed to preserve the information or if I had a logical error. And then what you see is as you increase the size of the code below like this point here, as you increase the size of the code, the logical error rate decreases. So this point here is like the error threshold, because it says that once you have a physical error rate that's like lower than the error threshold, I can reduce the logical error rate as much as I want by just increasing the size of the code. And we actually proved that like this kind of point should exist, but in the proof, it's hard to get a good bound on it. So you do numerics to get like a good bound on where this is. And then the second thing I just want to show you is that, so what we did is like, this is the error threshold plotted here. So like this point would be like this one. And then we vary like the number of error correction rounds. So we imagine we do like error correction, then more errors happen, we do it again, and we keep going. And we want to make sure that this like error threshold is stable, so it doesn't kind of decay. And you can see that like as you increase the number of rounds within the error bars, this is like very stable, which is nice, because in other kind of codes they saw like something more like this, where it kind of decayed and then kind of plateaued, but we really see just like essentially a straight line. So I think this code has like nice robustness, and this 1% value we get is actually reasonably, it's I think the Toric code in the same model would have a threshold of 3%, so it's not too far away. Okay, great. So I'll just conclude and then open up for questions. So what I wanted to tell you about today is that I think quantum error correction is kind of the main barrier still left to achieving useful quantum computing. And there's these overheads associated with it, and one of them is the time overhead from repeating stabilizer measurements. And a possible solution to this is to use a single shot error correction code. So then you only have to do one round of stabilizer measurements per error correction step. And then further things you could think about in this kind of arena is like more realistic error models. We're currently doing simulations with like this circuit level noise to try and get a better estimate of the error threshold. And then, at the end of the day, what do we want to reduce is not just the time overhead, but like the space time overhead. So the space as well. And you saw that the code I introduced here doesn't really reduce, it actually increases the space overhead compared to the 2D Toric code, because it's like a 3D lattice versus 2D. So the question is, can we like find more efficient protocols that reduce space and time overhead and allow us to build a quantum computer with far fewer qubits and with a fast logical clock speed? And this is the focus of my research and a lot of work going on this area. So yeah, I'll flash up some of the references. Yeah, I think for the recording. And yeah, then I just want to say thank you very much for your attention, and yeah, welcome any questions.
Great, thanks a lot, Mike, for the very clear talk. So I guess you can write the questions in the chat, but maybe let me start with one. So in all this that you said, especially in this part of the single shot, I guess you always have to make the assumption that all this process of measuring the syndrome and finding the actual operation of that corrects the error and so on happens fast enough so that no error happens in the meantime. Is there some way around this, or is this a given?
Yeah, that's a very good question, in that like I'm telling you like a classical algorithm to find the recovery operator, but in practice, like what's the kind of speed I would need to do this at? It's like the measurement time in like a superconducting qubit is like a microsecond of order of that. So then I need to be like solving this problem like every microsecond, which is like quite a big that's quite a big time constraint. But there's good news in that there's been very nice work by Oscar Higgett and Craig Gidney on making like the matching decoder very, very, very fast. So it's essentially fast enough to do it, I would say, to solve the problem fast enough. But there are some complications in that, like, okay, if your qubits are in the fridge, in like a dilution fridge, then you probably don't have time to run like a line out of the fridge to your computer and back in. So you then need to like do some electronics in the fridge, but then you kind of run into like cooling issues as well. So like this real-time error correction problem is definitely you can't dismiss it, but I think there's been nice progress on it recently. Okay. Yes.
And I guess also you have not said anything about the implementing gates, but that's a whole other problem, right?
Yeah, so yeah, that's the kind of thing I swept under the rug, is that we have an error correcting code. I told you about Pauli operators that we can do, but in general, we want to do a universal set of logic gates, and there's various constructions to do this, to you kind of want to do the gates in a fault tolerant way, which kind of loosely means I preserve the protection of the code. And there's lots of research on how best to do this, and it's still like I mean, in the code that I showed you, you can do a lot of them using this kind of transversal ansatz where you do like this tensor product structure. And so I think in our code it's reasonably okay to do the gates, but like that's also something you always have to like work out for whatever you're proposing is how am I going to do a universal gate set, and you also don't want to like have this, but you want this to be as fast as possible as well.
Mm-hmm. Yeah, makes sense. Yeah, thanks. There's a question in the chat. So 3D codes demand physical qubits to be placed actually in 3 dimensions. So I guess the question is where the code is in 3 dimensions.
Yeah, that's a great question. So, you know, like a superconducting architecture, you imagine they have like a 2D layout of a chip. So like, how do they do on the 3D code? And that's definitely like a drawback in some ways. But I would say actually there's been very recently very nice progress in a particular platform of neutral atom quantum computing, where they have the ability to kind of, they have these atoms in the trap and they can rearrange them at will. And so then they can like effectively realize 3D connections because they can kind of move layers around each other. So that's one example. And also photonics, which is, you know, something I think about quite a lot when I work for Xanadu, they're like building a 3D connectivity is not too hard because it's essentially just about kind of routing some fibers. And there the constraint is more about like, I don't want too many fibers like going into one chip, but it doesn't really matter if the topology I want to do is like a 3D or 2D. That's not the main constraint. Mm-hmm. So it's not as, there are some platforms where it wouldn't be as relevant, but I think there's actually been recently more and more platforms where this could be possible.
Yeah, so there's another question. Does the 3D code improve imposing periodic boundary conditions and also for dimensions?
Yeah, so actually, yeah, this is a kind of a subtle point, but with this subsystem code model, you get this property where if I put the model on a 3D, like a 3 torus, then I actually lose my encoded information. And this is a bit similar to how the honeycomb model, Kitaya's honeycomb model, if you put that on like on a 2 torus, you'd get like no ground state degeneracy. So these subsystem codes have this slight strange properties, and it's not exactly the same as the stabilizer code where you'd expect the number of encoded qubits to go like the genus of the manifold. So yeah, you can't naively do that. Although the kind of recent work on Floquet codes, if you've heard of those, is a way of kind of getting logical qubits even in this case. And in the 4D case, yes, there exist examples, and actually in the appendix of the paper, there's like a discussion of this. So that the model we can generalize to arbitrary dimensions actually. And so yeah, in 4D you maybe I mean, your kind of stabilizers get a bit heavier, so the threshold probably goes down a bit, but maybe you might have some nice gate constructions, and yeah, the model generalizes to arbitrary dimension.
But is there hope to do a coding for a 4D code with like with a photonic setup or with the neutral atoms and so on, maybe with more complicated arrangements? Or?
I think it would be possible. I mean, already like yeah. I mean, in photonics, I don't think it would be. It's more like the question is like, can you show that it would be advantageous enough? So like, if you can show like, okay, this has like a higher loss tolerance or something than the 2D code, then sure. I don't think that wouldn't, but it's you know, that the other thing about the 2D surface code is this: it's very hard to beat in just terms of raw threshold. There's not many codes that kind of have better logical error rates. So you have to, but if you can show that what your 4D code does, then there wouldn't be too much barrier to building it, I think.
Makes sense. Okay, so there's another question. Where's coming from the 30 for the? I'm not sure.
Yeah. So I think you're talking about, like I said, that you want kind of like code distance of 30 for like applications, and the way you can sort of get that is like, so I'll write a bit. So you have like I mean, you can show to first order that, like, let's assume that we're like below threshold. So P is less than P threshold here. Then the logical error rate kind of goes like something like this. So I have my physical error rate raised to the power code distance over 2, and then you know I just say like, okay, I want like P fail you know, to be like 10 to the minus 15. And then when you like, so that there's probably, I don't want to say something, there's probably like a constant here or something. So, but then this kind of implies that D is like 30, something like that. So this is where it's coming from. And but you know, depending on like what you want this to be, you'll have a different value for this.
Mm-hmm. Okay, I think there's a question being written at the moment. So. Okay, so just for curiosity, the 913 code that you drew, is it the old source code?
Yeah. So no, actually not. It's a different code. It's like the smallest surface code that can correct one error, but it's like related to the shortcode. So there's this like work on what's called compass codes, like 2D compass codes, which come from this compass model in condensed matter. And then you can show, so this gives you like a family of codes. And this surface code I drew is like one of the compass codes, but the shortcode would be like another one. So there are some like relations between them, but it's a slightly different definition.
Mm-hmm. Okay. Okay, I think there's more coming again. No, it's not a question. It's thanking you for the talk. Yeah, so I guess maybe that's this. Since there are no more questions, I guess this is a good point to stop. Yeah, so thanks a lot, Mike, for the very clear talk and for answering all the questions. I think we learned quite a few things about error correction. And yeah, thanks everyone for coming.
Thank you.